Welcome to part 2 of the repair of this PDP 1104's console. In the previous video I found a fault in the front console itself and in the terminator card over there, and was left looking at the last remaining faulty part, which is this M7859 interface card, which is controlled by a little 8008 microprocessor down here. And even though I had a better block diagram and mucking around with the scope and even a logic analyzer, I found myself getting nowhere, because this thing's madly controlling everything and trying to work out what it's doing, while at the same time trying to work out which part is failing and stopping it do its job was just too complex. But then I realised, well, hang on, this little chip here can control this entire board, or almost all of it. So if I remove it and drive its pins with my own signals, I should be able to do anything that that chip can do. And that enables a very systematic, organised approach to finding the fault in there. I can start off with the simplest signals that just get to the first level of that's required before any subsequent levels, and gradually, bit by bit, expand how much of this board that I've investigated until I find the fault. I made quite a lot of progress with that approach. I didn't do it here in the processor box, because I didn't want the fan running and having to dig around in here with probes and things. So I made a standalone system for testing the board, which I'll show you now. So here's my development contraption. There's the good board, which I'm using to experiment on. No point mucking around with the failing one until I know what I'm doing on a good one. As you can see, the microprocessor has been removed, and I've got a ribbon cable going over to an Arduino. Now this is powered by just an ATX computer power supply, which I've mounted on a board with rubber foots. I think I should have done that long ago. It's quite handy. You've got 12 volts, 5 volts, 3.3 volts, -5, -12. Yeah, just a good standalone contraption for jobs like this. It needs to be that big because this thing draws 3 amps. You can't run it off just a 7805 regulator, so which of course this thing can easily supply 25 amps, so that's okay. I don't have any edge connectors. Well, I do, but I didn't want to muck around with it with a good backplane, so I just wired up all that 5 volts into 4 parallel lots, and I'm injecting it at these capacitors. I don't know, I assume they're all connected internally, but I didn't want to put all the current through just one set of traces, so I'm using all 4, and not this capacitor of course, because that's for the -15 volts. We don't want to connect to that. And there's a ground coming off that loom for the oscilloscope, and a ground here to the Arduino. Curiously, this 8008 CPU does not have a ground pin. It has +5 volts and -9, and somehow it's referencing its signals to, I guess, the 5 volts, making sure that it when it wants to output a 0, it puts 5 volts less than the 5 volt supply out. It's rather curious. A microprocessor without a ground pin. Now, not all of them are needed. There's the 8 data pins here and a few control signals there, and they go to an Arduino Nano and just a bunch of resistors for protection. Now that's pretty rough and flimsy. I thought it would be quite flaky, but it's turned out quite reliable. But in interim I have made a little circuit board, so I'm going to put all that on a circuit board so it's a bit more robust, but that's proved to be quite robust enough. One of the inputs on there is also a probe, because the software I've developed wants to check signals against what the Arduino is putting into the processor there, so it's got its own little probe signal. The connector, you used to be able to get, a million years ago you could get things like this, where you could join a ribbon cable to a socket that would go, a plug that would go into a chip socket, although usually with the cable coming out to the side, but can't find any these days. But as it turns out, the processor on this is in a machine socket, and machine sockets plug into each other, so I've just used one of those as the plug. And these are, I think, male DuPont connectors, and I've just soldered them onto, plugged them into the tops of this socket, soldered them, and then hot snotted it all together for stability, and it just plugs in quite well, works very well. Now, a few of the chips get fairly warm, particularly that one of the ROM chips I've noticed, so I have a fan running off the 12 volts to cool it down. I was thinking maybe I should get this assembly and put a couple of blocks under there to make it, say, a couple of inches off the deck, and then stick this is just sitting in there, by the way, just a couple of bits of wood to keep it in place, and put a big hole there and have this fan underneath blowing into the hole onto the bottom of the board, and I'm pretty sure that would keep things cool enough. But even there it seems to be okay. It puts out quite a bit of wind, that little thing. So that's my test rig, and I've got some software in there that takes commands from here to drive the pins and read them back, and some software on the PC to coordinate it all. So I'll show you how that software works. While I was developing in that standalone system, I thought I'd better check that I haven't done any damage to that known good board. So I put it back in here to see if everything worked, and I turned it on, and it worked for a second, and then it went stupid. It actually started to show the same faults as this bad board was showing. And then I smelt some electrical burning smell, and I thought, oh hell. So I started peeling the board. I couldn't find anything hot, and I checked down here, and one of the chips on the terminator card was quite hot. So I turned it off, and I don't know if you can see it, but that chip there has got a blister on it. It had got quite hot. Now, I don't think that had anything to do with my previous repair of this board, but yeah, that chip's definitely cactus. So now I'm doing, for now, until I replace that, which is an 8837, I think, until I replace that, I'm using the known good terminator card from the PDP 1104, 34. Alright, now that we've loaded the firmware from Arduino, we can connect using this program. And there's a number of predefined tests, and there's also the option of doing some manual stuff. We'll get to that later. These tests first check out the basic stuff before moving on to more and more complex things that rely on the basic stuff being operational. So for instance, preliminary test passes because it was just doing the stuff that was in the manual, checking that there was 9 volts on the microcontroller and that the interrupt line was high and that it had clock signals. Now we come to this thing. The first thing it does is just checks that this bus here to the microprocessor isn't being driven all the time by this transceiver, so it should be able to apply the pull-ups on the Arduino to lift those lines up, and that should be the only thing affecting the voltage on those lines. So we'll just run that, and all the comms going to the Arduino are shown here. I'll describe that in a bit. Yeah, it's just checking that it can send anything on those lines using the pull-ups, so we know that this isn't holding the bus down. Next step is to fool around with the signals going into this decoder. I won't go into those because you have to sit there with your oscilloscope. Let's just go straight on to the more complex steps, and if they didn't work, then obviously you'd have to go back to these earlier steps. But let's upload the ROM contents. So run the tests, start, And there's the addresses. Here it's showing the what it's uploaded in hex and octal, and notice how it's all zeros. I have to build a test into this, which is to make sure that the bloody thing's turned on. So now we have power on the 7859, and let's try this again. This computer power supply is just starting to get a noisy fan after I gave it a nice little home to live on. Right. Starting again, and now we're getting some data, and I can tell you that's the right data. It takes a little while, not particularly fast. This idiot power supply is starting to make noises. Good thing they're cheap, isn't it? And there's two blocks of ROM. One lives at address 0 and the other lives at address 800 hex. In between there's lots of images, so to the processor there, one flows into the next. And it's just getting to the end of the first ROM at 1FF, and then switches to the second ROM at 800. And we're just coming up to the end of the ROM at 9FF, and then it will compare it to a reference copy, which has been checked against the listing in the manual, and it is exactly the same, so we can be confident that the ROM is good. It's also dumped that in both hex and octal to a disk file. That was good. Now we can try testing the RAM. There's only 16 bytes of RAM on this thing, and what it's doing is writing these values: 0, FF, OF, F0, 55, AA to each location. It writes all those values and then moves on to the next location. It checks that it can read them back each time. Now we're up to location F, which is the last one. Then it does a random data write, where it fills the 16 bytes with random data all in one hit, then goes back and reads it out and makes sure that it's the same random data that it wrote in, and then repeats. So it's doing the fixed value writes, and then it will do the random write again, and down here we can see how many times it's been through the loop. Number test 2 should just complete. There we go. So the RAM's working, and we can stop the test and mark it as a pass or a fail. Put that down as a passed. Now for the next set of tests we need the console connected, so I'll plug that in. There's the console connected with this cable into the board. Right, so first test is the indicator test. Run it, and all it does is make these bottom 3 LEDs count in a binary sequence. They're not in order. This is obviously the low order bit, and then that's the next one, and this is the highest order, changes less frequently. Next test is the numeric display, so we'll stop that test, passed. Go to the numeric display test, run that, and it just goes through all 8 values on each of the 6 digits. So that looks good. We'll stop that with a pass. The next one is a keyboard test. Now we have to readjust for that. Okay, keyboard test. Run that, and it shows us a display of the keypad, and then as I press keys it should light up the corresponding key over there. And notice this is scanning, because the scanning of the keyboard also drives the multiplexing of the display, so you're going to get that. And you can do multiple keys, so every key I hold down. Anyway, so we can check that each key works. It's not particularly fast scanning, so you've got to hold it down for a second or so. and they're all working. So that passes. The next test, which I'm just starting to work on, is the switch register test, where, looking at the block diagram, so well, before we go on to that, so what we've tested so far in that lot is the MCU, all the decoding stuff, the RAM, the ROM. For the display we were going to the indicators, that one, and for the display and the keypad, well, we had to use the bus register for the display, and for the keypad we had to read inputs there. So we've covered a fair bit of the board. The next thing would be the switch register, where we can load a value into there, but to read it back we have to go via the unibus and then read it in along that bus. But these are open collector outputs, so it needs pull-ups. It needs to be in the bus with a terminator card in order to see the values that have been written to the switch register. So that has to be done in the system. I think I'll leave that for now. I might actually test my broken board now. I think I've got enough to... I think, in fact I'm certain, that the test I've got here will uncover the area of fault in the broken board. So let's try him. Something else I forgot to mention, if you look down here, there's a resistor across there from pin 3 of that chip to the +5 volts. That's a pull-up resistor for the DC low signal from the unibus. Without that, the board doesn't initialize. So because I don't have a bus, I couldn't put that resistor on the back. You can probably even live in the system with that resistor. It's 220 ohms. The pull down for that, it's driven from the power supply by an open drain FET, and there's no pull up for it on this board. There's no pull up for it in the schematics of the power supply or of the backplane, so I don't know where the resistor is that would normally pull that up. There must be one somewhere, but bugger if I know where it is. But for testing this board, it had to be put on there. Another test that I should have shown is using this probe, is to test this PROM, read out its contents. It's critical because 5 of the address lines go into that, and it generates a number of signals that control the rest of the board, and in particular one of them goes into this decoder, which generates a whole lot more signals, so the contents of that have to be correct. So this test works by going through each of the addresses on the pin, all 32, and recording, having you probe one of the output pins here with this, and it checks that it's got 4 samples that give the same reading on this pin for the 32 locations, and then it asks you to move on to the next pin and so on until you've done all 8, and then it's got an image of what's in that ROM. It asks you to press a key when you've put the probe on the pin, and it will beep when it's got its 4 samples to tell you to move on to the next pin. And that PROM is this one, E34 and 82S123, and the 8 output pins to test are 1 through 7 here, and then the 8th one is pin 9 over there. So I'll do that test. Running the decoder PROM upload test, which asks us to put this probe onto pins of E34, this PROM here. We'll say, okay, run this test, and it says, you sure? Yeah, I'm sure. Now I've got to put this on pin 1 of E34, which is this guy and then press enter. I've got to hold the probe there till it beeps. There it goes. And put on to the next one. And press enter. It's going through all 32 locations and recording the value of the probe for all 32, and then it's doing it 4 times. When it's got 4 consistent outputs for that probe for all addresses, it moves on to the next one. We have bugs. Now, using the working M7859 board, I've been able to exercise most of this stuff, well, this stuff here and there, this, but the switch register and other things, and down here with the unibus, requires it to be plugged into the backplane. Rather than proceed with that, which is worth doing one day, certainly the faults in the bad board are within the area already explored. So I am just going to repeat the tests I've already done on the good board on the bad board and see what results we get. So it's now plugged in. I'm using an analog crow because the digital crow annoyed me with its the time it took to acquire samples. And that might be just because I'm not using it properly. I'm not that good at it. This thing I know at least. Right, so the obvious thing to do is run a few of the tests. I'll do the ones that don't need any sort of probing first off. The easy one is this bus free test, which just checks that the MCU can use its pull-ups to drive that bus. In other words, nothing else is holding it in any particular way. So it's just checking that it's free, and it is. These other things all require probing until we go to program ROM upload and try and read the contents of the program PROM. Now, a lot of those values look very familiar. OD in the first location, and these ones up here look right. It's, this laptop's considerably slower than the desktop system I was using to develop all this, so I'll speed up over all this right to the end of this download. And just about to finish, and it's saying mismatches. Alright, that's enough of that. Obviously we're having troubles reading from the PROM, which is hardly surprising. This board does not work. Let's try the RAM test. And we're getting errors there too. So we're exercising the address bus, the ROM, the RAM, and implicitly the decoders and the address loading logic, some of that and some of that. None of this down here yet. So the next simplest thing to check, which requires probing, is to make sure that the data we put on the bus from the MCU gets out here. So we're just checking the drivers in those transceivers. So that's the next thing to do. In the schematics, that is checking that these things can drive onto there, which is the bus that goes to the address register over here. MCU bus receivers will run that test and probe inputs to the address register, which is here. And it's sending increasing numbers to the address register, so we'll get a set of square waves between 12, 12, 4, 5, 4. Okay, this thing's being stupid at me. Alright, so it is getting from here to here. Now we've got to check that it's loading into the address register properly. Now the next thing to test is address register load. Now what this does is presents alternating hex 55 and AA to that and to there, and then loads them into the lower half and the upper half of the address register. So we just should see alternating bits out here. There's what's going in to one of the bits on the address register. If I look at it on any of them, it goes in on pin 13 and should come out on pin 15. And there's what's going in, and what comes out on pin 15 is nothing. Got a bit of strobing issue with the camera, but there's pin 13 going into one of the chips. Nothing coming out on pin 15. If we look at the clock signal, it should be latching it. You can see there are spots at the top. So it's getting that signal, but the problem is this one, pin 1, it's low. That's the clear signal. That should be high. That's why it's not loading into the address register. So what's going on here? This covers pretty much everything that's relevant here. What we've been trying to do is confirm that data gets from the CPU pins through these drivers onto the address bus, but it's not getting to the address register, because even though we're providing the clock signals on pin 9, which come from there and there, which are these guys, the clear signal on pin 1 is low, which comes from here, and it's stopping the registers. Well, they might be loading, but it's holding them at 0 output. The signals involved in doing that come from this timing state decoder, which come from the 3 state bits, and what I'm doing here is loading, is presenting the data for the low byte, and then hitting this clock signal, which means setting KY11 TS1L, this signal here, then presenting the alternate data for the top half of the address register and hitting that signal. So it's outputting 2 codes, ding 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 ding, and a third intermediate code, which is an inactive. Normally it's inactive, which is, I believe, TS5 low rather, because one of those bits has to be on, because there's 8 possibilities and there's 3 input bits. Yeah, the inactive state, I believe, is the TS5. So it puts that on, loads the data, hits TS1, goes back to TS5, puts up the data for the other half of the address register, hits TS2, and then returns to the inactive with TS5. That clear signal is set by T1L, which is this guy, and reset by that one. Now, I run into trouble with this stuff right from the beginning. Now that clear signal that seems to be resetting the address register and stopping the low values into it comes from here, and it's driven by this flip-flop. At the start of this test, and in fact all tests, because I want to get it into a known state, I'm bouncing that signal there, which sets the flip-flop, actually clears it, but we want a low output, to clear the shift register, the address register, and then bounce this signal, which presets it to high, so that then the address register is cleared and ready to be loaded. But for some reason this signal is not staying high once we start writing values to it. And the only way that can happen, as far as looking at the circuit, is by this signal here going low, but you can't see it. I'm only ever, once I've done that initialisation, I'm only ever hitting TS1 and 2, which go into here and here, which come out here and here, and which load the two halves of the address register. They should not cause this to go low, unless there's some glitch getting into the picture. But let's just look at the output of this, the pin 5 on that flip-flop, and see how it behaves when I run this test. Okay, it's low at the moment, not sure why, but we'll run that address register load test. You see it pops up, but it didn't stay up. Stop the test. Now it's at the end, it initialises it back to high. If I run it again, it should drop low, pop back up and stay up. And again, it bounces down, bounces up, but something makes it drop down again. Once more. Now my suspicion is that this could be caused by the way I'm setting these state bits, and perhaps the good board is just not sensitive to that. So this could all be a perfect. If it's just down to a glitch caused by the way I'm setting these bits, then if I fix that, this problem should go away, and I'm back to square one trying to find the fault on this board. And the problem is that two of these bits are on one of the Arduino ports and the third one's on another port. So it's impossible to set all three bits simultaneously, and therefore in between there's a potential for the wrong state to be selected out here, and it might be that one that triggers him. So the solution to that is to rejig this Arduino business so that those three bits are on the same port and can be set at once, and then there's very little possibility of a glitch getting through and upsetting. I'll just verify that this nonsense that we're seeing there is not happening on the good board, just as a sanity check, and then come back to the Arduino and rearrange the pinouts so that those three state bits are on the same port. Right, I'm on the good board again, and I just want to verify that the strange behaviour of this flip-flop when I do the address register load test, I just want to verify that this isn't misbehaving like it does on the faulty board. For some reason that I reset it, then set it so that it's cleared the address register but then returns this high so that I can now start loading things. Well, that's what it should do, but on the bad board it seems to be clearing this flip-flop, which brings on the clear signal to the address register and stops it working. Just want to make sure that that's not happening with this board. And we're looking at pin 5 on that chip. We're looking at the output there, pin 5 of the flip-flop. That probe there. For some reason, which I have not got to the bottom of, this software does not talk to the Arduino unless I first reload the software into the Arduino. Don't know why that is. Nano, old bootloader, COM4, good stuff. Upload. Problem uploading the board. Why? Am I not disconnected? I have not disconnected. Okay, assume that's done. Now I can connect here. Good. Address register load test. Should go low, then go high and stay high. Right, run the test. And it's high. Stop the test. Run it again, it'll pop low and then stop once more, pops low and then goes up. Oh, let's look at it again. One more time, goes low, then up. So, it's not happening on the good board. Is that just because this isn't sensitive to some glitch, or is there really something wrong on the other board in this circuitry? Don't know yet. Right, here we are with the original board. The Arduino setup has been rejigged to put all the state control bits on the same I/O port. I've just uploaded the modified firmware, and we'll do a sanity check that this still operates as it should, and we'll also look at that same output on the flip-flop. So quickly do the upload of the ROM test, and we'll flash through this to the end. Notice how the clear line for the address register coming from that flip-flop has been high the whole time. It does dip when it switches to the second half, but that's just because it's doing its initialization again. Okay, that finished successfully, and one more quick little test is the RAM. No, it only does initialization once. Alright, so that's working. Yes, so that's working. This appears to be behaving as before. Time to try it on the faulty board. Right, here we are with the faulty board. Notice no chips there. And let's just see, I'm really expecting the same nonsense, but let's find out. ROM upload, watching there, should bounce and then go high again. Oh, it did. No, we weren't really. Now let's see. Oh no. Aha. What does this mean? If this comes out successful, see that's behaving now, so it must have been the glitch I was suspecting. If this comes out to be reading properly, then why doesn't this board work? Interesting. That's actually looking pretty good, because when it was faulty there was lots of ODs, which is what you'd expect when the address register is being cleared all the time. You'd pick up the value in location 0 very often. So yeah, but there's far less of the OD value that there is now than there was. That was a blip that happened just because we switched to the second half of the ROM. Nearing the end. Let's see if we've got a good image. Beauty. Alright, that's interesting. Try the RAM test. Writing the fixed values down here to each location, and then we'll do a random test to all locations. But it's not complaining about any faulty values. Ka-ding. Right, so it would appear that the difference between these two boards so far is that this one's more sensitive to glitches when you don't set its state bits properly. Well, that's interesting. So does that mean that it would now appear that all this stuff here is working there, and maybe even, well, I've actually measured that already, and that does work, that PROM. It does have the same values as the other one. Maybe some of these signals are dodgy, or maybe the problem is just with the console, which involves writing to this bus address register and then those values going out to the display, because it did respond to the keyboard, so it sort of makes sense that the program was running, and maybe a problem there with reading from the keys there, but I'm suspecting something around here now. So let's hook up the console and do the tests for that. Right, now with the console connected and putting this cable in the right way, we'll do the indicator test. bounces these three around in a binary sequence. It's working. Alright, now for the numeric display test. Now that's playing up. We're never seeing a 0, but it is selecting the digits, and it's not showing, it's never showing 0 or 1, is it? 0 or 1, 4 or 5. Oh, we'll stop that and cogitate about that in a minute, but let's just quickly try the keypad test. Keypad seems to be working. Definitely something strange about these digits here. We'll think about a better way to test that. Those all the digits for this, both the code, the 3-bit code, comes out of here, and the 6 scan lines, but they're obviously working because it's going through in the sequence there, and both for the keypad test and for the numeric display it did move the sequence along, so those 6 are working properly. There might be something dodgy with those 3 lines there, but I'm more inclined to suspect it's just, no, it wouldn't happen for all digits, though, would it? No, it can't be a dodgy sockets. There's got to be something funny there. Might be some bad bits in him. If that's not the problem, then it might be further into the area that hasn't been explored, which surprises me. Might have to go down to the switch register and the unibus. But no, we don't need to. This stuff should have worked. It's got to be in this area, or the selecting of the bits in there, perhaps. No, that's probably working too. I'm going to have a little think. Now when I start this program, we go, instead of to this testing page, we go to this manual page. You'll see there's a lot of gibberish in those text boxes. They're actually little mini scripts, and this one, if I press send on that, watch the display. So that's actually sending, that script actually sends the commands to run through that display, and I won't go into too much detail on how that works at the moment, but basically I'll separate into its constituent parts. That says start a loop, run it 6 times. This here tells it to turn on one of the 6 digits. Then start an inner loop, run it 8 times. And this tells it what code to send to the digit that's been selected by the outer loop. The dot tells it to wait a 1/10 of a second and then close the inner loop, close the outer loop. And if I change that dot to a underscore, in fact 2 underscores, the underscore means stop for a second, so now it's going to stop for 2 seconds after changing each digit value. And if we run that, 2, 3, 2, 3, 6, 7, 6, 7. So there's what's wrong with it, and if you look at what was going on there, there's what it should be showing. There's the digit, the binary code for those digits. Here's what we were seeing. And you'll see 2, that bit is a 0, but it should be a 0, it is a 1. Same again there, same again there. So this middle bit is stuck on. Now, does that explain why it didn't work in the computer with the microprocessor on the board? Because it seemed a lot more nuttier than just simply not displaying that properly. So I guess that depends on where the bad bit is. We know it's not. The bad bit can't be in the address register, otherwise we wouldn't get ROM and RAM tests working, it's got to be here or here. But would that fault cause the problems that we get when we install it in the computer? I'm not sure it would. Anyway, so I'm going to try and track down exactly where it's failing. I can use this scripting bizzo to do that. So we're suspicious of this bus register not setting those 3 bits there that go to the console and select the value to be shown in each digit. These 6 lines here select which digit, these 3 select what that digit will display. And they come from the second 8 bits of this bus address register. So looking at the schematic, there's the first 8, there's the second 8. So, and you can see there, KY6 num 1, 2, 3, they're the 3 bits that go to the console. So if we look at the inputs of this guy, and then the outputs, we should see if he's failing. And what I've done over here, I've put in this little scriptoid here, says start a loop. There's no value straight after the square bracket, so it just repeats indefinitely. The R5200 tells it to write a 0 to the right 00 to that second 8 bits of the bus address register. The 5207 tells it to write 07 to that second byte. So we're turning those 3 numeric bits off and then on, and then looping around. So if we look at the pin numbers if we look at the pin numbers there, it's 4, sorry, yeah there. Look at the pin numbers, it's 4, 5 and 12 should come out on 2, 7 and 10. So looking at the oscilloscope, that was E73, which is this guy here. So if we look at pins, what were they again? Pins 4, 5 and 12. So pin 4, bouncing up and down. Pin 5, likewise. Pin 12, 9, 10, 11, 12. And pin 13 is the 4th bit, which we're keeping a 0 all the time. So that's a bit of a sanity check. We've got the right bits coming to the right place. Now let's look at the outputs, which for those 3 bits are 2, 7 and 10. Pin 2 bouncing as it should. Pin 7 not bouncing. And this goes through an inverter before it goes to the console. That's why we're always getting a 1 at the console. And the last bit was 10, 9, 10, and he's bouncing. So this guy at 74175 is cactus. If we look at it, he's like the same as the address register, 74175. If you look at pin 1, which is his clear, that's nice and high as it should be. And his pin 9 is his load signal, billions of little pulses. So that's working, or rather the inputs to it are working, but it's not. And in anticipation of all the problems I might get, I bought a bazillion chips. Anyone need any 74F02s? I've got 100 of them for about $3 or $4, so they were cheap. And a selection of other chips involved, and in amongst them is 74175. So I shall remove him, and I also bought sockets because I want to cut him off. I don't want to try and desolder him whole. I'm going to cut his pins and pull them out individually to minimise damage to the board, and replace it with a socket and stick one of them in and see how it behaves then. Well, never am I going to do that again. As you can see, I managed to break a few traces while trying to get the pins out. I think next time I have to do one of these, I will just snip off the chip like that and just solder the new IC onto the existing pins from the previous chip, and not try and desolder the pins from the board, because DEC uses such tiny little donuts, such thin traces, and it's not as if this stuff's high density. They could make them much thicker, but they're far too delicate. So I use bits of wire wrap wire to extend those broken traces out to the pins and then just solder them up onto the pins. I decided to put the chip in directly rather than with a socket, because if I do have to pull it out again, it's going to be easier to do it with the pins than with a socket. Anyway, time to see if it works. We'll just do that same test as before, see that I can toggle those bits on the input and that they reflect through to the output. Now, I did have this horrible thought: what if that chip wasn't broken? What if the output is held high because it's shorted to something, the trace coming out of it is shorted to something, or if the input of the chip it goes to is broken and holding it high. But here's hoping that's not the case. Okay, so the inputs are 4, 5 and 12. 4 toggling, 5 toggling, 12 is toggling, so I've at least soldered those pins correctly. 2, right, that output's getting there, and 7 is the one we're interested in. Yay! It's toggling too. 9, 10. And there's the clock signal going into it, the latch signal. Good stuff. And pin 1 is high, as it should be. So that looks good. Now, let's find out if that fixes the problem when it's in the computer. So there it is, back in the PDP 1104. It is the one that was faulty, right? Didn't have those 2 chips there. And I've reinstalled his microprocessor. I'll apply power to the frame. So, applying power. Still nonsense. Still not well. Why is that? No, there's still something wrong. Okay. Looks like there's going to be a part 3 video. Bugger. I think I'll make that Arduino thing on a proper circuit board to make it a lot more robust, because from here on in I'm going to have that in circuit, because obviously what's wrong is out here now to do with this. I've got to test the switch register and the unibus stuff, so it has to be in the back plane. So I don't want that flimsy bit of Arduino breadboard stuff there. I want to put it on a proper circuit board and join it in to the processor there. Damn, would have been nice, wouldn't it? Would have been nice if that fixed it. This video's gone on way too long, so I won't delay for whatever the final steps are and tack it on the end of this. I'll make a part 3. And I hope you enjoyed. I hope you find this interesting. Subscribe if you did, give it a like if you did, and catch you later.